Everyone, I'm Neeraj Srivastav. I'm here to present my project, which is skin cancer classification using convolutional neural network. So I'm going to be covering these areas as part of today's presentation, mentioned in table of contents, introduction, and why this project is interesting, data set analysis and challenges, data pre-processing steps, model architecture, experimentations that were performed, and another technique that I applied called synthetic minority oversampling technique uh, for melanoma cancer detection, comprehensive multi-model evaluation and results, potential next steps and future work, related work literature review, and the citations. Introduction. Well, the project focuses on developing an automated deep learning system for multi-class classification of 9 distinct type of skin lesions, out of which 3 are benign in the sense are cancerous. Skin cancer represents a significant global health challenge, with melanoma alone counting for 75% of the skin cancer related death, despite comprising only a small fraction of cases. So, an early and accurate detection is going to be critical for patient outcomes and saving lives. The project addresses several fundamental challenges inherent to medical image classification, like severe class imbalance and visual similarity between the classes. So, as part of this project, in order to handle these challenges, I experimented with multiple models. Started off with the baseline CNN, then explored DenseNet 201, MobileNet V2, Inception V3. These are all transfer learning models, and I experimented, and the results are part of this presentation. Now, why this project is interesting, as I said, right, is the intersection of deep learning and healthcare. The project addresses one of the dermatology's most challenging diagnostics problem using computational innovation at the intersection of transformative deep learning and high stakes healthcare. It is challenging because the skin lesions, not all of them are cancerous, and they have a high visual similarity, right? Comprehensive comparative methodology. The study established a baseline CNN and rigorously tested 3 different transfer learning architectures like DenseNet, MobileNet, Inception V3. The project demonstrated the synthetic oversampling SMOT functionality, which is basically about generating synthetic data, is fundamentally flawed. It creates artificial interpolations that do not preserve diagnostic features in the model, learns them incorrectly. This project has a real significant world impact. The system could democratize expert level skin cancer screening, especially in undeserved or underprivileged areas, and thereby making a great difference to the world. Right now, talking about the data set, I used a data set from International Skin Imaging Collaboration, ISIC. It is available as part of the Kaggle data set. Now, there are 9 distinct skin lesions, as I mentioned, out of which top 3 here mentions are malignant, which means are cancerous. And the one here, actinic keratosis, is precancerous, and rest all are non-cancerous, but still problematic. So the objective is to build a CNN model to predict one of these kinds, 9 skin lesions, distinguishing between each of them. Data set challenges: class imbalance. There is a severe class imbalance. As for some of these classes, the total image count is not even 100, as you can see in this table below, and there are only 2,358 images, which is definitely not enough. High visual similarity between classes, and it was also evident in the confusion matrix when it was printed for various models. It significantly misclassified multiple skin lesions, right? And there were false negatives on melanoma, which were misclassified as nevus benign. And this can potentially delay cancer diagnosis. And some of these examples are mentioned here. As you can see, melanoma, 4 images, and then here nevus, 4 images, and they kind of look very similar, making it hard to distinguish, right? Now, as part of the data pre-processing, which is a very important step in this case, the data augmentation pipeline had these number of steps, like, for example, random flip, random rotation plus or minus 43 degrees, makes model rotation invariant. Lesions do not always appear upright. So it's important. Random zoom 12 plus or minus 12% simulates different camera distances and lesion sizes. Random translation plus or minus 6%. Lesions are not always perfectly centered in photos. That's why. And random contrast plus or minus 12% accounting for different lighting conditions and camera settings. And then for transfer learning models like DenseNet, MobileNet, Inception, it's important to normalize the pixel value from 0 to 55 to DenseNet expected range for optimal feature extraction. Now, talking about the model architecture, I started off with a baseline model architecture. As you can see here, the baseline model is a simple convolutional network model designed as a lightweight trainable from scratch as an architecture. It consists of three sequential convolutional blocks for feature extraction, followed by the fully connected layers for classification. Now, talking about the table here, so layers, we have 7 layers. Layer 1, 2, 3 accepts, it starts with, as an input layer which accepts RGB image and uses the first convolutional block, followed by max pooling to extract basic patterns like edges and corners. And then we have hierarchical abstractions that were performed from layer 4 to 7, where the repeated application of convolutional blocks and max pooling further captures complex structure, textures, and simple images, and identifies high-level visual concepts. Now, when it comes to layer 8, which is flattening, the process concludes the feature extraction phase by using a flattened layer to convert the 2D feature maps into a single one-dimensional feature vector, preparing the data for the fully connected layers. Now, finally, for the output, dense layer learns non-linear combination of the extracted expected features. A dropout layer is implemented to randomly deactivate neurons, serving as a crucial regularization step to reduce overfitting. The final dense layer uses a softmax activation function to output a probability distribution across uh, all target classes. Now, when it comes to hyperparameters, as I mentioned, input shape or RGB is resized to 75 by 100 pixels. It uses the Adam optimizer. Learning rate is 0.001. Sparse categorical cross entropy is used as a loss function with a batch size of 32, and total training epochs were 25 that were performed. Class weights to handle the class imbalance, class weights are applied in the range 0.98 to 1.03. Model checkpoint was added to save the best model based on the validation accuracy, and an early stopping was introduced in case validation loss does not improve for 6 epochs. And reduce LR on plateau helps reduce the learning rate by factor of 0.5 when validation loss plateaus. When it comes to the DenseNet architecture, and the core is utilizes a pre-trained and it is characterized by dense blocks where each layer is connected to a every other layer in a feed forward manner, promoting feature reuse and mitigating the vanishing gradient problem. Now, talking a little bit about this architecture, the core is a frozen pre-trained DenseNet 201 that extracts a 1920 dimensional feature using global average pooling. Now, when it comes to layers 4 to 8, where pretty much the normalization and stabilization is performed, batch normalization layers are used to stabilize training dynamic. And when it comes to feature learning, a dense layer with ReLU activation and L2 regularization is applied to learn task-specific feature from dense nut output. For overfitting control, two dropout layers were added with rates 0.5 and 0.3 to robustly prevent overfitting during training. And when it comes to the layer line, the final dense layer uses softmax function, activation function to produce a normalized probability distribution across all target classes. Now, Inception V3 and MobileNet, I'm not going to go into those that much of a detail because these two models didn't perform very well. But to talk a little bit about it very quickly, Inception V3 is designated for high accuracy with efficient computation using the Inception module. It employs a parallel convolutional path to capture multi-scale features simultaneously. It uses one by one convolutional as bottleneck layers to reduce dimensionality and computational cost. MobileNet V2 architecture is optimized for resource-constrained environment with low latency and a small footprint. It's built around inverted residual blocks with depth-wise separable convolutions, splits convolution into depth-wise and point-wise operations. Now, when it comes to the experimentation phase, I started with a baseline CNN model. The model was trained for 15 epochs, as it is evident from these training plots here, using the Adam optimizer with the initial learning rate of 0.001, by also applying the pre-processing techniques that I mentioned before. Now, talking about these plots, training accuracy, as you can see, it shot up from roughly 27% in the first epoch to by 40% in the third epoch itself. The training accuracy eventually plateaued at around 62%, as you can see from the chart. By the epoch 15, training ROS decreased nicely and smoothly, dropping from 2.5 to about 1.06. The validation accuracy followed a similar track, climbed to 37 to 42% range, and eventually settled around 43% by the epoch 12. This persistent gap between training and validation metric, combined with the instability seen in the validation loss, points to the model is struggling to generalize, most likely because of the challenges posed by the severe class imbalance in the data set. Now, when it comes to some of the metrics like confusion metrics and accuracy, the simple CNN test metrics, as you can see here, the test accuracy is around 36.44%. The baseline CNN model achieved, as I mentioned, 36.44% accuracy with a macro averaged precision of 0.395 and a macro average recall of 0.359 and a macro average F1 score of 0.299, demonstrating poor performance, particularly on minority class where melanoma and dermatofibroma had 0% recall. Nevus, as you can see, achieved the strongest performance of 14 out of 16 correct, 87.5% recall, followed by pigmented benign keratosis of 12 by 16. 12 out of 16 were classified correctly, right? Now, when it comes to DenseNet model experimentation to overcome the poor performance of baseline CNN, we adopted a transfer learning approach using DenseNet 201, a deep convolutional model pre-trained on ImageNet, as I described earlier. The training accuracy improved from 20% to 65% over the course of training. Validation accuracy peaked at 52 to 54% around mid-training, then declined to 38 to 40% towards later. Training loss also decreased steadily from 2.7 to 1. The generalization gap, which is around 25%, widens after 18 to 20 epochs, as you can see in this chart. Best model performance likely occurs after epoch 18, supporting the use of early stopping. Now, DenseNet confusion metrics and accuracy. DenseNet model achieved a text accuracy of 44.92%, representing only 8 which is still better, 8.48% absolute improvement over the baseline 36.44. The model performed well on several classes. Nevis achieved the highest recall with, as you can see, 14 out of 16 correct predictions. Melanoma also showed stable and clinically meaningful performance with 10 out of 16 very classified cases, right? But still not clinically, I would say, valid, because you cannot afford to have only 62.5% of correct classifications, right? It must be at least above 80%. Now, moving on to MobileNet V2 experimentation, it didn't really perform well on this data set. Looks like it's not even it's not designed for such type of classification. Test accuracy is 27.97%. And MobileNet achieved an accuracy at reaching a peak validation accuracy of 48.96 by epoch 2, indicating that transfer learning was initially effective. It continued to rise and then steadily declined, and evaluation on the held out test set revealed a catastrophic collapse to 27.97%. Inception E3 V3 actually performed even more poorly. The overall accuracy was 21.9%, and there's results, and you can see some of the other numbers here are available. I don't want to obviously go for every single statistics in the interest of time, but this results imply a fundamental mismatch between Inception V3's multi-scale parallel feature extraction and the requirement of dermatoscopic image analysis. Now, there is another technique I applied because since the data size was less than 2,000 some images, so I thought let me give it a try with the SMOT, which is about synthetic minor oversampling technique, which generates synthetic samples, which is what is mentioned. I have mentioned as an example here. These are some of the samples generated by SMOT for melanoma. Now, because melanoma cases are highly underrepresented in ICE's dataset, I thought of using this SMOT technique that can generate certain synthetic sample data. Now, by using this model, you're essentially doing a binary classification where you have melanoma and rest everything as non-melanoma, right? Now, on the held out test set, the model showed the mixed result. It achieved 72.9% accuracy, 50% recall, and 25% precision, and a USU of 0.71, correctly identifying 8 out of 16 melanomas. While this demonstrates some ability to distinguish melanoma from non-melanoma, the model still missed half of the melanoma cases and produced many false positives. This level of performance is far below critical expectation, where sensitivity typically needs to exceed 80 to 90%. And most likely explanation is that SMOT, relies basically pixel level interpolation and does not preserve medically meaningful features such as asymmetry, border irregularity, and pigment structure, which is very important. Now, overall results of all the model, as you can see here, DenseNet dominated every single metric, establishing itself as the most optimal architecture for this task. Test accuracy of over 44.92%, 8.48% better than baseline, and 112% better than inception, and 60.6% better than MobileNet. While the simple CNN baseline also achieved a respectable second place with 36.44%, that and it's also in demonstrating that straightforward architecture with adequate capacity can learn meaningful representation when trained from scratch on focused data set. And Inception V3 and then the MobileNet actually performed very poorly. I don't want to dive more into the details of that, but I would say overall, all the models fell short of the clinical deployment requirement, which typically mandates greater than 80% sensitivity for cancer detection and greater than equal to 70% specificity to minimize false positives. Talking about related work literature review, there were a number of other research papers I looked at, and two of the most prominent ones I'm going to be mentioning here. First one is the skin lesion classification with the deep learning, which is like a benchmark research paper in the model for such type of work. It was performed by Shandel and team. It kind of established the benchmark. As I said, it utilized HAM 10,000 data set, which was carefully curated by a team of experts from different hospitals. It became the undisputed gold standard for comparing deep learning algorithm in skin lesions classification. Is also access source for critical challenge. While the dataset enabled robust training, its structure formally revealed and quantified the severe class imbalance problem inherent in real world dermatology. Shandel and team demonstrated that conventional CNNs and transfer learning could achieve dermatologist level accuracy on the majority well represented classes, providing a crucial baseline performance expected for this field, and is directly relevant to my current study, and that's what I have mentioned here. Now, DenseNet in medical imaging is another very important research paper because, as we observe, DenseNet performs very well on this type of a data set. It effectively mitigates the vanishing gradient problem and ensures a strong gradient flow throughout the entire network. It promotes feature reuse, leading to significantly fewer parameters compared to traditional CNNs, making it highly efficient. This efficiency is critical when deploying models in resource constrained clinical settings on mobile devices. It is the critical utility for it served as a critical utility for medical imaging. The architecture excels at preserving low-level subtle features, edges, textures, fine patterns through deep layers, features that are often critical for accurate dermatoscopic diagnosis, and it is one of the reasons why it was a motivation for my current study. Now, potential next steps and future work, data centric improvement and model refinement. I think there is a huge scope for this model to evolve and can be a great contribution for the medical community. And the way I look at it is, if I combine the ISIS data set and the HAM 10,000 and various other data set I mentioned like BC and 20,000, this will increase the training data from current size of 2,500 to over 30,000, and can dramatically improve representation of the current minority class melanoma, which is actually cancerous. And advanced model tuning and ensembling, I would like to then further use DenseNet 201 on this data set using conservative progressive fine tuning and focal loss, implement and then I'll try to implement ensemble methods for improving stability and reliability. I would also like to explore generative AI to generate certain synthetic data and then explore how best it can augment the test data. And then when it comes to the next steps, like I do see potential for deploying this over the web, so that as a user friendly web application where you can just upload an image and see the what are the predictions. And then I would like to share that publicly with at least with the dermatologist and medical fraternity to then verify if this model is indeed working as expected, and then continue to improve upon. And if we definitely pursue this seriously, then there is a significant opportunity I see for submitting for an FDA approval. And then eventually, you see, the whole idea is it should democratize expert level skin cancer screening to reduce diagnostic delays and save lives in the underprivileged or underreserved areas, right? Now, when it comes to citations, these are the six citations that I would like to refer. There are many, but these were some of the most prominent ones that I looked at, like skin lesion classification using CNN with patch-based attention and diagnosis guided loss weight by Gezert and team, comparison of ML algorithms used for skin cancer diagnosis by Biston and team, skin lesion classification with deep learning by Shandel and team, DenseNet in medical imaging by Hyong and team, SMOTE variants and medical imaging by Fernandez A and team, comprehensive survey of CNN architecture for skin cancer by Hansel and team. So that's a wrap up of my presentation. Thank you very much for the opportunity.